Hello everyone, welcome back. Um, in this video, we'll be solving three more challenges of the microcorruption, which are the White Horse Challenge, the Muddy Video, and the Johannesburg. Now, here's the thing: these three challenges are about the same topic, which is exploiting a vulnerability in the code could lead to a that could lead the program to return to a place that we wanted to return to. For example, it could be an unlock their function, it could be our custom code or whatever. So it's basically some kind of practice of the buffer overflow video that you have watched, when we try to overflow the stack and return basically to a place that we wanted to. So yes, so before I forgot, don't forget to follow me on Twitter and join the Discord server. Yes, so let's not waste too much time and start solving them. So one more thing before I start solving the challenges is you have to try the challenges on your own. Try them on your own, and if you get stuck, you can just watch the video and learn something new. In all cases, you can just watch the video and just follow me and grasp the way that I think about the challenges and the way that I'm approaching them basically. So yes, so we start with White Horse. So what do we have? So overview. So this lock is attached to the lock ID Pro HSM2, which is the hardware security module 2. So this is basically an advanced hardware security module more than the one. So the hardware security module 1 is pretty simple, where you have to simply just pass the password, and it's gonna be checking if that password is right or wrong, and then set a flag into 0 or 1 based on the result. So the hardware security module 2 is more advanced than that, and it's not going to be setting a 1 or 0. You can just check that on the manual if you want. So we have updated the lock firmware to connect with this hardware security module. Okay, cool. So if we try to connect, or just try to dynamically see what this program is doing on the card. So what do we have? So enter the password to continue. Again, the same thing. So if we try, for example, let's just try to send them, for example, item wide 123. Program no longer running. CPU must now be reset, and the password is not correct. So basically, it's checking for a simple password. Um, yes, let's try to statically now reverse engineer what we have in our hands. So basically, this is an conditional unlock door function. This is the main, which is the interesting part. So main is gonna be calling login. Okay, if we try to search for the login, so this is the login function. So it's adding a negative value to the stack pointer. Then he's moving the messages for the puts functions. Then okay, so this is basically just simple output and the screen. Just we can see that, for example, in here. Nothing special. We saw them in a lot of challenges. Next we are moving 0x30, which is um, 16 multiplied by 3, which is 48 bytes of data. That's 48, so we are basically moving 48s into register 14, so register 14 is going to be 0x30. Then we are moving what's in the stack pointer to the register 15. And then we are reading something, so we are reading the password. So we are basically reading 48 bytes into the top of the stack. Since we are passing down the stack pointer as an argument, we are basically reading the password at the top of the stack. Next, we are moving what's at the top of the stack. Um, we are moving what's at the top of the stack into the register 15, then calling the conditional unlock door. So the conditional unlock door is going to be using the hardware security module 2, which we do not know how basically it's working from the inside, since we don't have the code of the hardware security module 2. So it's going to be returning the result and the register 15, which then he will be using to test if the register 15 is 0. So we jump if it is a 0 to the log n plus 0x2e, which is this one, which will be basically printing for us that the password is not correct. And if the register 15 is having a 1, then we will be having access to the door, and access will be granted. So the thing is, if we take a look at such a code from a perspective of someone who is trying to break into this, we do not know the password of the hardware security module 2, since the password is inside of the hardware security module 2, and we don't have access to the hardware security module 2, so it's impossible to find out the password. So we gotta find a way on how we can exploit this program to, for example, unlock the door. So here's the idea. So the idea is to basically try to craft some code, basically that can open up the door, and then try to make the login function to return to that code. Which means, for example, this login function, once it completes executing its code, it will be returning. That's right. And then it will be basically, once it returns back, it will be returning to the main function. So it's gonna be continuing the execution from the 44.3c instruction. So the thing is, if we make the login function, instead of returning to this 44.3c instruction, we need it to be more, let's say, accurate and return to the code that we will be crafting. So the first step we have is to try to, let's say, just figure out where the return address is exactly, and then how much data we have to send in order to override that return address. And then we have to craft some kind of code that can open up the door for us. So if we try to do all of that, basically we can um, just set a breakpoint, for example, before we call the conditional unlock door. We are basically gonna be passing the stack pointer, right? So if we try to set a breakpoint at this address, which is this one, and try to see exactly where the password is in the stack, and then try to calculate the offset of that password from the return address of the login function, then we will be sure that we can override that return address and return to our code that we will be crafting after that. So if we break this address, so basically if we break this address and we continue, so we have to reset and we continue. So basically, wait a second. This is not the address that I want. Did I copy something wrong? 4428. Anyway, let me just set it manually. So wait a second. Where's the login? Yeah, here it is. I don't know. I think I just set up the breakpoint. Like, it was a mistake. Anyway, yeah. So if we give the password, for example, ironbyte123, we hit the breakpoint. Cool. Now, if we try to figure out where the iron byte is in the stack, so here's the iron byte. It is 69 and so on. So the return address should be 44.3c. So this is 44.3c, but it's, since we are using literal Indian, it should be in the reverse order. Yes, so this is the return address. So how much data do we need to send to get to the return address? So basically, we need to send um, 2 bytes, 4 bytes, 8 bytes, 10 bytes, um, 12 bytes, 14 bytes, 16 bytes. And then we set the return address to a place that we will be seeing next in the next step. So this is basically what we need. So the thing is now we should be returning to a place where we could set our code. So here's the idea. We can set the code in this place and make the login function return to the top of the stack to execute the code that we will be creating. that or the code that we will be crafting. So here's the thing. Now let's try to craft some code that can open up the door for us. So for example, to open up the door, we can just push 0x7f and then call basically the interrupt function. So the interrupt function, we should try, for example, to find the address of the interrupt. So the address of the interrupt is 4532. So this is the 4532, and then we basically need to return, since the return is not supported by the assembler. We should just find a simple return in here, which is this one. We'll be using later on, which is 3041. So if you assemble that, so this is the assembly. Now if we get that and we add um, 3041, if we disassemble that, we get this code. So this is the code that will be unlocking the door for us. Now if we try to send that code, for example, if we reset, if we continue, we check the hex encoded input. If we set that, now as we can see, this is the code that we have sent, which is this one. Now this is the code, and we have now to overflow 2 bytes, 4 bytes, and 6 bytes to get to the return address. So here's how we can craft this payload. If we send this input, so this is basically the payload. This is the payload that we will be using to unlock the door. So if we send the payload plus how much, so we can just, for example, this is length of the payload. So length of the payload is going to be length of that payload. Which problem, payload is not defined. Wait a second. Yes, because I mistake it there a little. Yeah. So this is the payload. If we try that again, so length of payload is cool. Okay, so basically the length of the payload should be length of the payload divided by 2, simply because we are using hexadecimal characters and each 2 characters are basically 1 byte. Yeah, so basically now we send the payload plus 41, which stands for some random data, for example A in our case, uh, multiplied by 16, basically, since we need to overflow 16 bytes to get to the return address, minus the length of the payload, plus basically now the return address, which is, in our case, we should be returning to the top of the stack, which is 38. This is 0, which is 10, then 11, then 12. So basically this is the address of 3812, which is, if we revert them, basically we don't have to revert them, we can just write them directly. So 38 and 12. So if we try to send that and see what's going to be happening, so let's check them before we try to execute. So this is the payload that's going to be executed. This is just filling the space, and this is the return address. Now here's the thing: if we try to set, for example, another breakpoint before we return, we step. Now, if we step a little, we hit the return address. Now let's see if he's going to be using that return address. He didn't use it. Why? Simply because the little Indian. I have to inverse the address of the return in order to make the CPU understand exactly that we want to jump to that address. It is simply because of the little endian. I have to reverse the order of the address, or the order of the bytes exactly. Now if we reset and we continue again, now if we try that again, now it should be working. Yes, now he's executing the code, as you can see. So this is the push 0x7f. This is the call. If we continue, he obviously unlocked the door. So basically, this is how we can do it. So if we solve it now in the server, we can just send that. and good job. We have basically solved the White House now. The White Horse, I'm sorry. So the thing that we have understood is that we basically tried to craft some code that can unlock the door, and then we return to that code. So basically this is a simple return. Now in real world applications, or let's say for example on binaries that work on your computer, there is already a mitigation that can mitigate that, which is the NX, which means that we cannot execute code on the stack. So it's a kind of mitigation that you have in binaries that can, for example, um, prevent code from being executed on the stack. But on the MSP for 430, I suppose when they have corrupted the challenge, they didn't actually set any kind of boundaries on how you can execute the code, or can you execute the code or not. So let's move on to the next challenge. So Mari video. So we have the developers have written the code to conform to the internal secure development process. So this lock is attached to the lock ID Pro HSM2. So the same hardware security module too. So if we try to continue, we see that passwords are between 8 and 16 characters. So we send, for example, 41, 41, 41, 41, 41, whatever. If we continue, the password is not correct. If we try to reverse engineer the code statically, let's see what's happening inside there. The first thing we should be trying to find is the main. So this is the main. So we have the login function. So this is the login function. So if we try to find it out, so this is the login. So same usual messages, enter the password to continue. Remember, passwords are between 8 and 16. So this is the how he's gonna be reading the password. So he's gonna be reading register 14 is gonna be having the size of the password, which is 0x30, which is 48 bytes of data. What else? So register 15 will be having this address, which is a typical address that we have used a lot, which is 2400. And then he's gonna be using a pretty famous function, which is this str copy function. So for those who don't know what the str copy is doing, so str copy is going to be copying data from one address to another address. So this is basically the source, which is 0x2400, and this is basically going to be the destination, which is the stack pointer. So he's going to be copying the password that we have give um, from this address, which is 2400, to the stack pointer, to the top of the stack pointer, basically. What else? Then once he do that, he basically start to initialize um, some data, basically some address exactly. He's gonna be memory setting that to 0. So this is the again this is the source, which is 0, and this is gonna be and the size, which is 0x64. 0x64. So basically once he let's say transfer the data of the password from the address 2400 to the top of the stack pointer, he's gonna be freeing that address from the characters that we have give. Let's say delete the password from that address. So that's gonna be deleting the password from 2400. So, and this is the destination, which is 0x2400. Yes. So then he's gonna be just deleting the password from 2400. Yes. So what do we have? So now once he do that, he basically moves what's at the top of the stack pointer to the conditional unlock door, which we do not know how it really functions because we do not know the internals of the hardware security module too. And then if the result is 1, then he's gonna be opening up the door for us. Otherwise he's gonna be printing for us that password is not correct. Now, how can we approach such a thing? How can we find a vulnerability in that code? Now, as we can see, we can do the same methodology as we did with the white horse, but there is a little trick in here. So the trick is with the str copy. Let me explain that to you more carefully, just by trying to, let's say for example, I'm gonna try to use the latest um, I'm gonna try to use the latest payload. So for example, the latest payload have this one, which is the unlock function door. Let me try let me try to put that payload at the top of the stack. Let's try just to load that payload at the top of the stack and see what's gonna be happening. So if we reset that, if we before we do that, I need to set a breakpoint. Let's set a breakpoint before the conditional unlock door, as we have did with the latest challenge. So yeah, if we send that, let's try to check that. So as we can see, we have 13, 12, 7F, 0, 0, and then the rest of the payload. This is the payload. The rest of the payload is not there. It's not at the top of the stack. And this is basically the return address that we have to override. This is basically the return address that we have to override. Now here's the thing. We cannot have the rest of the payload at the top of the stack, which is weird, right? Now, the reason that we do not have the rest of the payload or our payload at the top of the stack is basically because of the str copy. Now, if you go back and try, for example, to open up, let's say, for example, I'm going to open up the manual of the str copy just to understand how the str copy is working exactly. So if you read about the str copy, it says that these functions copy the string pointed to by the source into a string at the buffer pointed by the destination, and the programmer is responsible for allocating a destination buffer large enough, that is, which is the string length obviously of the source plus one, for the difference between the two functions. See the return value. So this is basically what the str copy is doing. Now the thing about str copy, guys, let's just make it very simple. There is a little trick about the str copy that says it will be stopping the copy, or stop copying the data from the source to the destination when it hits a byte equals to 0. And the thing about our payload is that we have 13. Let me just try to put that, for example, in here so that you can see it more clearly. So this is the payload. If I'm gonna be zooming a little for you, so this is the payload. Those are the bytes that's gonna be copied to that destination. And as you can see, there is a 0 here. So when the str copy is gonna be copying from the source to the destination, it's not gonna be copying all this because it hits a 0, and by hitting a 0 it understands that this is the end of the string. So that's why the payload that we have crafted in the white horse challenge is not gonna be used. We cannot use it now. We either have to find a way on how we can obfuscate, for example, the string into, for example, we can obfuscate that 0, make it, for example, another thing, and then when it's loaded, when it's loaded on runtime, we decrypt it into another thing that's gonna be executed. We can use obfuscation to make this code um, executable. And the thing is, we can, for example, pack it and then unpack it on runtime. This is a simple way, for example. But we can do, for example, another trick to open up the door for this challenge. So the trick, guys, is that we can, for example, call this function the interrupt function. So the interrupt function is, what does the interrupt function is doing exactly? So it's taking the number of the interrupt that's going to be using. In our case, to unlock the door, we need to use the interrupt 0x7f. And then it also needs the call. So we need to call it with that interrupt. So basically to do it, we have already created that. So basically to call it, we need to push that and to call that. Now, if we try to return to the interrupt function, what if we try to return to that interrupt function without calling it? We can return to it, right? So if we try to return to that function, we can return to that function, and so it's basically like that. We return to, um, we try to, for example, if we try to overflow that buffer, so for example, or we can overflow that and then return how much data do we need to send? We need to send 16 bytes again. So those are 15 plus 2, which are 16 bytes. So if we send 16 bytes and then we return to the interrupt, and then here's the thing, the interrupt function is gonna be moving what's at the stack pointer plus 2 to the register 14. So if we try to already overflow that, set the return address, and then set 2 random bytes, and then set the 0x7f, then the interrupt should load the 0x7f to the interrupt and call the 0x7 interrupt and unlock the door for us. So to be more specific, so basically we're going to be sending 16 bytes of uh, random bytes, or just random data, plus the address of the interrupt, plus 2 bytes, 2 random bytes, just to make the interrupt jump this 2, because basically this is what the interrupt is going to be executing. So the interrupt, when we call the interrupt, it's basically going to be moving what's in the stack pointer plus 2. Basically register 15 is going to be what's in the stack pointer plus 0x2. So we need to jump 2 bytes in order to get the interrupt number. So this is basically what the interrupt is going to be using. So basically when I try to call it, so I'm going to be returning to the interrupt function, and when the interrupt function starts executing, it needs to get the interrupt number from the stack pointer plus 0x2. So that's why I'm going to be adding 2 random bytes to make the interrupt function obviously jump those 2 random bytes, and then basically just pass on 0x7f, which are that's 7f, 007f. This is basically what I'm gonna be doing. So basically I need to inverse the order, obviously because it's little Indian. And yes, so this is basically the payload that we need to send. So if we try to craft that on Python, so for example we need to we can just create that just directly. So 41 by 16 plus the return address, which is of the interrupt, which is 45 for C, which is 4C 45, and then we add just some random data, which is 41, just 2 random bytes, plus the 7F00, which means that when the interrupt is gonna be called or returned to, it's gonna be obviously fetching this 7F00, so it's gonna be jumping this 2. So this is the jump that's gonna be happening, and then it's gonna be using the 7F00 as a way, as an interrupt number to just unlock the door for us. So if we try to do that, try to use that, so we obviously need to reset. We continue again. We send that. We hit the breakpoint. So this is the 41. This is the 4C45, the return address. Those are the 2 random bytes, and this is the 7F. Let's see now in practice how this is gonna be happening. So I'm gonna be setting another breakpoint before we return. If we continue and then we now step, so this is the address that's going to be returning to. So if we step again, so it's starting to execute the code of the interrupt, as we can see. So this is the 0x2. You see, this is the stack pointer, the actual stack pointer plus 2. You're going to be passing that to the register 14, I'm sorry. So if we step, if we try to see what the register 14 now is having, it's having 0x7f, as you can see. And if we continue, we obviously just unlock the door. So I hope you learned something just out of that. Now if we try to solve that, good job. We have solved Monty video too. Now the latest The latest challenge on this video is really interesting too. So Johannesburg. So Johannesburg is obviously a firmware. They just have updated the firmware and said that they will be rejecting passwords that are too long. So this lock is attached to the Lock ID Pro Hardware Security Module 1. Okay. If we continue, let's try to see one, let's say for example 41 41 41 41 41. The password is not correct, but for example let's try to give him a password that is too long, since he said that he will be rejecting passwords that are too long. Let's see, if I for example send him a lot of A's, the password is not correct, invalid password length, password too long. I think in this challenge, guys, there is a really interesting thing, which is, we will see. Let's try to obviously try again to reverse engineer the code statically just to understand what's happening. Okay, so if you search for the main, okay, so this is the main. So it's obviously as the same challenges. It's gonna be calling the login function, and then if we try to see what the login function is having, so the same usual thing, the same messages, and then we have um, the function that's going to be reading the password. This time you are reading much more data. You are reading much more data than usual. We have 3F instead, which is 63 bytes. Size of data to be read is equal to 63 bytes, and this is the address that's gonna be he's gonna be using to load the data. What else do we have? So we have the test password valid, which gonna be used as a way to obviously check the password, and then he's gonna be unlocking the door. And there is another interesting thing, is that um, there is this function which is unlock door. Now, since we have a function that is unlock door, and at the same time we also have str copy that's going to be copying obviously the password to the top of the stack, password copying uh, password to top of stack, then passing down top of the stack. So register 15 is going to be having the address of the top of the stack. So obviously the thing, if we try to approach this challenge also, we see that there's this little thing, which is obviously after he tries to test if the password is valid or not. He also, so obviously if it's not valid, he's going to be jumping to this one, and he's also going to be checking if this byte so if the stack pointer plus 0x11 is equals to this byte. So if it's not, then he's gonna be saying invalid length, or password is too long, and he's gonna be printing that, and he's gonna be stopping the program from execution. Now here's the thing, this is a simple mitigation that he has tried to implement in order to stop us from overflowing the buffer that we have, and try to override the return address. So this is a simple mitigation that he tried. So this mitigation is pretty simple. I have already explained that on the buffer overflow video. So basically this is a simple canary that's going to be used to just check if someone is trying to smash the stack and change the return address of that stack frame, which is in our case the login function. So we can simply bypass that by passing that value. So basically, to understand more what I'm talking about, you can just see that in practice. So let's try to set a breakpoint there and see what's gonna be happening exactly. So before we test the password is valid, I'm gonna be setting a breakpoint there. I'm gonna be also setting a breakpoint before we return. So if we continue, so basically we have now the password. So I'm gonna be passing, for example, item byte 123. If I continue, so this is the item byte 123 that is in there. And it's also in here since he copied that item byte into this place, and this is the return address. And as you can see, before the return address there is this little byte. So this is our little canary that he will be using just to check if someone is trying to just override the return address and smash the stack. So we can simply, so here's the way, we can just simply send some random data, and when we get to this little canary, we pass the same canary as the one that he has, just by assuming, guys, just by assuming that this canary is not randomized. Because when this canary is getting randomized each time we run the program, then this is gonna be a problem. Why? Because I need to somehow find a way on how I can fetch it directly and automate the process. Otherwise, if it's not randomized, that each time that I reset is gonna be the same, so the same byte is gonna be the same, then everything is cool. Like we have, if this value is hard coded, then this is gonna be simple. So let's try to reset and check if that canary is the same or not. So if we reset again oh my god, I think I sent something weird. Let me just reset. I don't buy it. 123. I think it's gonna be the same. Yes, so it's the same canary, so it's pretty simple. Chance where we have just to overflow those, and then when we get to the canary, we send the same canary as the one that is in the stack, and then we set the return address to the unlock door function, and everything is cool, I think. So the payload is gonna be how much data do we need to send? So we need to send those are 12 bytes. Um, and those are 12 bytes, 14 bytes, and 16 bytes. So we have to send 41 by 16, obviously, plus 41 for this one, plus C0, and then we set the return address to the unlock function door, which is gonna be this one. If we try to see it, which is 4644, which is, oh my god, oh come on, 4644. Okay, and this one is gonna be 41C0, and we send that. So basically if we try that, okay, we need to reset again, check the hex encoded input. So we have 41, 41, 41, we have 41C0, and we have 4644. Now everything should be cool. Um, let's try, for example, guys, before we do it that way, let's try, for example, check if we have, I mean, I'm gonna be just doing a little check just to check if that value is really a canary or not, just from perspective of someone who didn't just, for example, try to reverse engineer statically the code and understood that this is a simple canary. Let's say, for example, to send 41 instead of a C0 and check if the return is gonna be happening or not. So if we reset, so continue again, we see again, and as you can see, the program has stopped from execution and the invalid password land password was too long, which means that this is really a canary that he has implemented there. So if we reset again, we start and we send this one, we continue. Then if we continue, we hit the end, which means that we are cool, we have bypassed that canary, since the value at that value is the same, which means we didn't change that value, we just set that value as the same value that was on the stack to make sure that the conversion goes well. Now if we step, if we return, we are cool, we are in the unlock door. Good job, we have just solved that too. We solved that. Oh yeah, cool. We have solved the three of them. Now, I hope you have learned something new. Don't forget to follow me on Twitter. Don't forget to join the Discord server. Don't forget to ask questions too. You can ask questions. You can do whatever you want. Yes. See ya in the next video, I suppose. The next video is gonna be cool. You should watch it.